parallelize tree search? Answer. We need to keep in mind that the best-2 data structure requires additional communication that is not explicit in the tree edges. Thus, it's convenient to add an additional task that corresponds to the best-2. It sends data to every tree node task and receives data from some of the leaves. This later view is convenient for shared memory but not so convenient for distributed memory. A natural way to agglomerate and map the task is to assign a subtree to each thread or process and have each thread or process carry out all the tasks in its subtree. For example, if we have 3 threads or processes as shown earlier and we, the subtree rooted at 0, 1 to thread or process 0, the subtree rooted at 0, 2 to thread or process 1 and the subtree rooted at 0, 3 to thread or process 2. What is the problem with depth-first search? Answer. The problem with depth-first search is that we expect a subtree whose root is deeper in the tree to require less work than a subtree whose root is higher up in the tree. So, we would probably get better load balance if we used something like breadth-first search to identify the subtrees. Why dynamic mapping scheme is used? Answer. A second issue we should consider is the problem of load imbalance. Although the use of breadth-first search ensures that all of our subtrees have approximately the same number of nodes, there is no guarantee that they all have the same amount of work. It's entirely impossible that one process or thread will have a subtree consisting of very expensive tools and as a consequence, it won't need to search very deeply into its assigned subtree. However, with our current static mapping of task to thread or process, this one thread or process will simply have to wait until the other threads or process are done. An alternative is to implement a dynamic mapping scheme. What are the principal differences between parallelizing the solvers using n-body solvers and p-threads? Answer. By default, local variables in p-threads are private. So, all shared variables are global in the p-thread version. The principal data structures in the p-thread version are identical to those in the OpenMP version. Vectors are two-dimensional arrays of doubles, and the mass, position and velocity of a single particle are stored in a struct. The forces are stored in an array of vectors. Startup for p-threads is basically the same as the startup for OpenMP. The main thread gets the command line arguments and allocates and initializes the principal data structures. The main difference between the p-threads and the OpenMP implementation is in the details of parallelizing the inner loops. Since p-threads has nothing analogous to a parallel for directive, we must explicitly determine which values of the loop variables correspond to each thread's calculation.
Please subscribe our channel for more videos and education.